All right. Hello, class. Um, Hope you guys are doing well. Hey, Chad. Thank you for your comment. Um, so today, we are going to start reviewing for the AP test. So, oh my gosh, one of my dogs just did a real stinker. Hazel, that's a big stinker. So, what we're going to do today is we're going to do some practice problems from the workbook. So let me first tell you how to find the AP Physics workbook. Okay. So College Board has released a gigantic, almost 400-page workbook for students to prepare for the AP test. And so that's what we're going to use to prepare. So if you go to the drive and you let's see, Dumpty Dum. Go to AP1 Physics courses. Come on. There we go. You go to test prep material. Test prep material. Come on. Why isn't it? Why isn't it opening? Come on. Well, I don't know why my computer isn't loading it. But if you go into that test prep materials folder, you go into AP1 and you'll find a copy of the gigantic document that I was talking about. Okay? So, what I've done is basically for the next few weeks, I'm going to do a couple pages of the workbook every day, and then I've given you guys a couple pages of the workbook every day. And so we should get a review of all the topics. Should be nice. So I'm going to kind of go backwards in terms of content. Okay, so we're going to start off with some DC circuits, and then we'll work our way all the way back to the beginning of the course. Okay. So if you want, when you submit your work for this week, if you want to type into the PDF and then just print it, like print a PDF of just the pages that you were assigned, that would be really nice. So what the workbook has is it has a bunch of scenarios, and for each scenario, it has some questions. Okay, so we're going to do the questions. So the first scenario involves a circuit with some light bulbs, and it says A circuit is constructed with identical light bulbs as shown at the right. And then it says quantitative analysis. Which switches must be open in order to have a completely open circuit? So an open circuit means that no current is flowing out of the battery, okay? And I think you can see that if any of the switches, 1, 2, or 3, is closed, then there's a path for current to go out of the battery and come back, okay? So the answer to that first part is that we have to have all the switches open. So I'm going to put an X. I'm going to move it right there. All switches open. Okay. Justify, I just justified it in words. Okay, so part B says which switches must be closed in order to have a short circuit. And I apologize if it takes me a while to answer some of these questions. This is my first time seeing the questions, so hopefully I know how to do them all. Which switches must be closed in order to have a short circuit? So a short circuit means you have current flowing out of the battery, but there's no resistance, okay? So we can see if we close switch 2, then current can flow out the battery through bulb 1, through bulb 2, and back to the battery, okay? So that would be a path with resistance. It would have the resistance of 2 bulbs. If we open switch 2 and we close switch 3, again, the current can flow out the battery through bulb 1, through bulb 3, and back to the battery. So that would be a pathway with resistance. However, if we close switch 1, then switch 1, the current will go out the battery, it'll go through switch 1, which has no resistance, and it'll come all the way back to the battery. So that would be a pathway with no resistance. So I'll put an X, and switch 1 must be closed in order to have a short circuit. Y, I'm going to say if switch 1 is closed, there is a zero resistance pathway for current flow. Okay. Boom. Is it possible to light bulb 2 without lighting bulb 3? Is it possible to light 2 without lighting bulb 3? I would say that the answer is yes. Quite obviously the answer is yes. If you want to light bulb 2 without bulb 3, as long as switch 3 is open, no current can go through bulb 3. So if switch 2 is closed, then current can flow through bulb 2. So what we want to do is we want to close switch 2 but leave switch 3 open. So let me type an answer to that. So the answer is yes, it is possible. How is it possible? What we want to do is close switch 2, but leave switch 3 open. in this case, current will flow out the battery through bulb 1, then bulb 2, then back to the battery. Okay, I think I can resize this. Let me resize this. Yeah, all right. Make sure that if you have any questions, put them in the live chat. Is it possible to light bulb 1 without lighting either bulb 1 or bulb 2? We can see that if current flows through bulb 1, okay, if current flows through bulb 1, current comes out the battery, it flows through bulb 1. To get back to the battery, the current has to flow through either bulb 1 or bulb 2. So it's impossible to light up bulb 1 without also lighting up either bulb 2 or bulb 3. So the answer to that is no. All right. And the reasoning is after current passes through bulb 1, the only way to get back to the battery is through bulb 2 or 3. All right. So I hope that that makes sense. All right. Oh, okay, so we're on to part E. Using representations. On the diagram to the right of the circuit with switches S2 and S3 closed, sketch in an ammeter so that you could correctly measure the current through bulb 2. Okay, so one of the things I taught you about ammeters is that for an ammeter to work properly, you have to have it in series with the device under test. So we want to place the ammeter in series with bulb 2. So let me see if I can figure out how to annotate this thing. Is this going to work? Ooh, cool. So there's an ammeter. And put A. That's supposed to be an A for an ammeter. So that's where you would put the ammeter. Part F says, on the diagram shown of the circuit with switches S2 and S3 closed, sketch in a voltmeter so that it would correctly measure the potential difference across bulb 1. So voltmeters, they need to go in parallel with the device under test. So I'm going to put a voltmeter in parallel. So, boom, boom, voltmeter. Kind of like that. Okay. So, that's the first scenario. Yay, we did the first scenario. So now let's go to the next scenario. It says a simple circuit is constructed with a single battery, a wire, and a single bulb with resistance R. Describe what happens to the total resistance of the circuit when a second identical bulb is placed in the circuit as shown below. Provide evidence. So I would say bulb B is in series with bulb A. Okay. The total resistance would then be RA plus RB, which is greater than RA. All right. So that's what I would say for that part. Write an expression for the total resistance of the circuit in terms of R, the resistance of a light bulb. That's very simple. The answer would just be 2R. Because if you put two identical resistors in series, it doubles the resistance. A third identical bulb is now added to the circuit. Fill in the following table to show what changes and what stays the same in each circuit after bulb C is added. Place a check mark or an X in the correct box. Okay. So the what does it say about what do we have here? The total change in voltage. Well, one of the things we'll notice here is that the three bulbs or two bulbs make a voltage divider circuit, okay? And in a voltage divider circuit, the resistors, the voltage of all the resistors adds up to equal the voltage of the battery. Doesn't matter how many resistors are in the voltage divider. Okay, so doesn't matter. Chad asked a question. Sorry, I missed that. With a voltmeter, it doesn't matter where the negative probe is. Actually, it does. You want the negative probe right before and the positive probe right after, or the positive probe just before and the negative probe right after. Okay, because we're measuring the voltage difference across the device. Okay. In some situations, you want to know what is the actual value of the voltage at a particular point in the circuit, in which case the negative probe should be connected to ground. But if you want to know the potential difference across a device, you put one on either side. Okay. So the total delta V is going to stay the same. Okay, because the voltage drop of 3 bulbs has to add up to V, the voltage drop of 2 bulbs has to add up to V. What's going to happen to the delta V across bulb A? So if we had 2 resistors, each one is going to get half of the voltage because they're equal in size. If we have 3 resistors, each one is going to get a third of the voltage. So the delta V across bulb A is going to go from half the voltage to a third. So that's decreasing. So this is going to decrease. All right. And similarly, the voltage across bulb B is going to decrease. Because it's also going to go from half the voltage to a third of the voltage of the battery. what's happening to the total current? Well, we added an additional resistor in series, so the total current is going to go down. Okay. Because we increased the resistance. What happened to the current through bulb A? Bulb A, again, the total resistance of the circuit went up. So that means that the current has to go down. So the current through bulb A goes down. I hope these questions seem really easy to you, because they seem really easy to me. Almost absurdly easy. Current through bulb B. Bulb B, it's just a series circuit. There's only one current in the entire circuit, so that's going to go down if we add resistance. Okay. And then lastly, what happened to the total resistance? Well, we added a resistor in series, so it went up.
Sorry, I missed that. Could you say?
I said series, and so my phone thought I was talking to it. Okay. Oh gosh, I hate these argumentation questions. They're so dumb. But let's go through it. So, your lab partner makes the following statements. Since power is equal to I squared R and brightness is proportional to power, the larger the resistance, the more power the bulbs will have and the brighter they will be. So we need to add more bulbs in series to make more light. Is Angela correct? Justify using the equations for power. And the table completed in part C. Well, I would actually say that the power output, here's what I would say. The power output of the battery is V squared over R. You guys have heard of that one too. It's the same as I squared R. But the thing about this R is it's the total resistance of the circuit. Okay? So what if we had N batteries? Okay, so instead of 3 batteries, what if we had 8 batteries? Then the total resistance would be 8R. So the power is going to be V squared over NR, where N is the number of bulbs. Okay? So that's the power output of the battery. So we can see as N increases, the power decreases. This means the bulbs get dimmer. Angela is wrong. Okay, so I'm trying to model how you might answer these questions if you were taking the AP exam. When we add more bulbs, the one closest to the negative terminal of the battery will be the brightest. The second and third bulbs will get fewer electrons because the first bulb will use up some of the electrons. Oh my gosh, Blake is really dense. Blake is a moron. So adding more bulbs in series won't make any more light. Okay. Blake, I'm sorry, Blake. Blake is really not very smart. Here's what I would say. All the bulbs will have equal brightness because they are in series. And series things have the same current. since P equals I squared R, and all bulbs have the same I and the same R, they're all just as bright. So yeah, Blake's answer is so goofy that I don't even know what else to say. I mean, bulbs don't use up electrons, because what would happen if a bulb used up electrons? That would mean that if bulbs are using up electrons, then that means that the bulbs are becoming negatively charged, which doesn't happen. That just doesn't make any sense at all. All right, so we did our 4 pages. Okay, so you guys are going to do page 258, 259, 258, page 259, page 256 through 259. Keep in mind that the page numbers are the page numbers down here, all right? So that's all I have for today. I hope you found those questions easy. I found them to be extremely easy. I'm the teacher, but they seem like at a very low level, those questions. So I think if you get that kind of a question on the AP exam, you should be able to do well. All right, have a really nice afternoon, and I will talk to you later.